Okay, so we've done some work on Born-Haber cycles, and that's given us some values for the lattice enthalpy. I'd just like to focus on lattice enthalpy for one lesson. The experimental values that we use in the Born-Haber cycle give us a value for the lattice enthalpy, if that's what we've worked out. So we've got experimental values from Born-Haber cycles. But there's another way of working out lattice enthalpy, and that's just basically using physics and maths. If we imagine that ions are these spheres and they're interacting with each other, you can use, I don't know, Coulomb's law, whatever it is. You can use the bits of physics that help you work out the attraction between these different charges. And you could calculate a theoretical a theoretical value. Now, theoretical value. The theoretical value uses something called the perfect ionic model. So that assumes that the ions, as they are perfect spheres. It assumes some other things as well, like the ions act as a point charge and so on. I don't want to get into that again. That's all very physicsy. But we can just focus on that. Ions are predicted to be perfect spheres, and if you put perfect spheres into the physics and the maths will return a value, you'll get the theoretical value for your lattice enthalpy. So let's have a look. Sodium chloride. So sodium chloride's experimental value, that's the Born-Haber value. Experimental value minus 786. Of course, that's the lattice formation enthalpy. Okay, the theoretical value using the perfect ionic model, so the pen and paper version, is minus 766. Okay, not exactly the same, but not bad. The difference there, it's less than 5%, isn't it? It's pretty small. So what does that tell us? Well, that tells us that in the theoretical calculation where we assumed that ions were perfect spheres, has given us pretty much the same answer as the experimental value. That tells us that the ions are probably pretty close to being perfect spheres. Yay. Okay. Now I've got a value for magnesium iodide. Okay, so experimental value first. Minus 2327. Okay, just before we go on, it's worth just taking a moment. 2327 is a lot bigger than 786. Why is magnesium iodide's lattice enthalpy so much bigger than sodium chloride's? Well, magnesium ions, they're about the same size as sodium ions, but of course a magnesium ion has a 2+ charge compared to sodium's 1+ charge. So twice as much charge means it's going to have twice as much attraction to the ions around it. So we'd expect a much bigger value there. Okay. So that's okay, but let's have a look at the theoretical value that assumes that all ions are perfect spheres. Minus 1944. Okay, now that is a very big difference. It's a difference of, I don't know, I haven't worked it out, but it's 20%, something like that. So it's an enormous difference for science, and it's one that we have to account for. What is it about magnesium iodide that means that its theoretical value is a long way out compared with its experimental value? Experimental value. Okay, what's going on here? Well, we're going to have to take a little bit of a detour here, because when we talk about atoms and ions and molecules and bonding, we tend to think of ionic bonding as being kind of one thing that happens with metals and non-metals, and covalent bonding as being a different thing that happens with non-metals only. But this is a little detour here, but if I go across the periodic table from sodium all the way to argon, and then if I make chlorides of those, I have sodium chloride, magnesium chloride, aluminium chloride, silicon chloride, phosphorus chloride, and so on. What I find is that over here we've got something completely ionic, and over here we have something completely covalent, perfectly covalent. What I mean by perfectly covalent is the pair of electrons shared by two chlorine atoms are absolutely perfectly shared. They are in the middle. But for sulfur chloride, well, of course, chlorine's a little bit more electronegative than sulfur, so we'd expect to see a little bit of charge difference there, wouldn't we? And phosphorus, again, there's an even bigger difference in electronegativity, so we'd expect to see bigger negative charges on the chlorines and a bigger positive charge on the phosphorus. So these are covalent molecules, but they are polar molecules, right? The electrons spend more time down with the chlorines than they do with the phosphorus or the sulfur in the middle. What if we go in the other direction? Well, magnesium chloride is also ionic, but aluminium chloride, yeah, it should be ionic, but it has some strange properties. It evaporates at quite a low temperature. It reacts violently with water. You wouldn't expect that from an ionic solid. So it's ionic with some covalent properties. And what about silicon chloride? Well, again, that's a covalent molecule, but it also has a very low melting point, also reacts violently with water. It's almost as if we've got ionic down one end and covalent down the other end, but in the middle, it's more of a spectrum kind of thing. As we go from one end ionic to the other end covalent, we go through a whole bunch of things which are a little bit ionic-y covalently in the middle. That's a roundabout way of saying that ionic and covalent are not opposites, they're not different types of bonding, they're opposite ends of a continuum that goes from one end where the electrons are completely given and taken to the other end where the electrons are completely shared, to a middle area where the electrons are kind of partly shared but also partly ionic. If we have an ionic compound where the electrons can also be shared sometimes, we say it has some covalent character. Covalent character means that there's both ionic bonding and covalent bonding going on at the same time. They both put a bit of bonding in the pot, if you like. And what does that mean? Well, covalent bonding is that's the strongest type of bonding there is, right? You look at diamond, it's entirely made up of covalent bonds and it's the strongest substance known. So if we add a bit of covalent bond to an already ionic compound, then that adds a bit of extra bonding. So what we see here is theoretically imagining magnesium iodide to be made of perfect ionic spheres. We have a value, it's quite a big value, but when we actually measure that value using experimental data, we find it's much, much bigger. So that's our first point. The actual value shows additional bonding from covalent character. Covalent character. Okay, so what is covalent character? Well, again, if I go back to sodium and chloride, we imagine that we've got perfect spheres, and so the perfect ionic model works. If I had a chlorine molecule, the chlorines are actually completely enveloped in a one molecular orbital, a big cloud of electrons that both chlorines are sharing. What do we get in the middle? Well, what we get is the small, highly charged magnesium ion can actually distort, well, it's iodide, isn't it? Can actually distort the cloud of the iodide ion, making it a bit covalenty. That's not a word. And the effect is magnified if the ion is bigger. So because the iodide ion is much bigger than the chloride ion, we'd expect the iodide ion to be much more polarized than the chloride ion can be. So the ion is polarized by the small, highly charged Mg2 plus ion. And that changes its shape, causing distortion. Now remember, the perfect ionic model works on the basis that ions are perfect spheres. If we start distorting them, they're no longer perfect spheres anymore, and the maths won't be quite as good at predicting the actual value. So there's quite a lot going on here. But one of the ways this question comes up is where you're given a bunch of molecules and you have to guess which of them has more covalent character or has the biggest difference between the experimental and the theoretical values. So what you're looking for is a big difference in size. Of the ions. And remember, positive ions, if we start with a positive, if we start with an atom of magnesium, when we make it into a positive ion, it's going to get smaller because we've taken electrons away from it. Whereas if we had a negative ion, we're giving it an extra electron, which means the cloud gets slightly larger. So negative ions are already bigger than positive ions from elements in the same period. But of course, if we drop down a couple of rows, iodide is right down there. What has it got? 53 electrons. So it's a much bigger atom already. Add another electron, it's an even bigger ion. So you're going to get a huge difference between the size of the magnesium and the size of the iodide. So big difference in size. And anything with which is a small, highly charged ion. So the small ions are usually going to be the positive ones. They don't have to be. Cesium plus would be fairly large positive ion. But small positive ions and then a large negative ion give you the best situation for some distortion, for some covalent character, and for a big difference in the values. So if I took aluminium iodide, I'd expect even more distortion because aluminium, and again, is an even smaller, more highly charged ion. Okay.